Good evening. I hope you guys are hanging in there with all these videos going through chapter 7 through 10. So this one is going to be on bonding and some factors on even the type of bonding or the bond length is going to be that they want to have minimal repulsion and maximum attraction that results in the lowest energy. Now, nature doesn't want to work very hard if it doesn't have to. So whenever it can maintain the lowest amount of energy, that's what it's going to do. So that's why it's going to decide between metallic, ionic, or covalent bonding for some of the elements in the situations that they are in. So the first one you can see here is metallic bonding is just a sea of electrons that move freely, responsible for all the properties of metals, like that they're ductile, they're shiny, they conduct electricity. We don't really study too much about metallic bonding because there really isn't anything more than that. Just a sea of electrons around the nucleus. They don't really have a pattern. It just creates all the properties that we have for metals. Then we have ionic bonding. All right, so for ionic bonding, I hope that you can think in your head and you know that it is a metal to a nonmetal, and they are trying to do this to gain stability. And so if it's a cation, that means that it has lost electrons, and if it's an anion, it has gained. Hopefully those are things that you remember from Chem 1. Now this is something that I do want to talk about is why they want to do that and how they stay together. And that all has to do with lattice energy. This is a new term. This is not anything that you saw before. So the only time you're going to apply lattice energy is when I can say, oh, it's ionic bonding. And again, that would be like NaCl, our table salt, sodium chloride. Sodium is a metal, chloride is a nonmetal, so it would fit our ionic bonding that they are going to transfer electrons, again, to minimize the repulsion and maximize the attraction. So how do we tell how much lattice energy we need? The first way is always going to be on charge, and the second way is going to be the size of the ions. The charge is the easiest thing, you guys. If you just look up, like I just said, sodium chloride, like I have over here, then it has +1, -1. And so the greater the charge between the positive and the negatives, between losing electrons and gaining electrons, results in greater lattice energy to form that solid. So I have sodium chloride versus magnesium sulfide. Well, I can easily see that as +1, -1, +2, -2, greater charge, greater lattice energy. So that means it's a lot more energy to take in and release in forming that ionic bond. Then I could have something that has different charges. So I can see sodium has +1, oxygen's -2, or I have something again that has the same charge. And this one again is going to require more lattice energy because the charge is higher on both, and thus it makes it less soluble. So if I look up above at this one that I started with, this is going to tell us that NaCl is going to be more soluble than magnesium sulfide because it doesn't take as much energy to dissolve. Okay, so let's say all my examples have the same charge. Then what am I going to do? Then I'm going to go to the size of the ions. And you can see I have sodium fluoride versus sodium chloride. Well, if I look at my periodic chart, I can see that the fluoride ion is a smaller ion. It's in the 2p sublevel versus the chlorine, chlorine, bromine, so that would be 3p. And so that means that the sodium fluoride is packed more tightly. Stronger bonded, greater lattice energy is going to be involved. Now, in all of these situations of ionic bonding, we need to think about that they are crystals. Really important to think about that. They're salt crystals. They have very high MP, melting point, and BP, not gasoline, boiling points, okay? And it also makes them good conductors because they're able to dissolve in water. So the crystals have high melting points, high boiling points, and they are good conductors. All right, so hopefully that helps you a little bit with lattice energy. Again, if you have any questions on that, make sure that you ask me about it. We will have some book questions on this too that you can kind of just look at, see my answers and be like, okay, I got that, that makes sense. All right, covalent bonding, I'm not really going to talk too much about that. You guys, I hope you listen to those intermolecular forces videos that were given by College Board. They do such a great job, and we talked a lot about this in one of our class periods versus our Zoom. So hopefully that all is going to make sense to you. Again, I think the biggest thing to remember is that the intermolecular forces, no matter what molecule you have, they all have LDF. So one way you always get a point is putting LDF. And then it's whether or not you have more than that with hydrogen bonding or dipole-dipole. Okay, that's it for this one. And then we have one left, you guys. Excellent. I will see you on the next one.